Hello and welcome to this Aerospace Testing International webinar. Today we're talking about modern metrology, the challenges and benefits of Industry 4.0. I'm Ben Sampson, editor of Aerospace Testing International magazine and the host of this webinar. In the next hour, we're going to hear from two leading experts in metrology about the digital transformation happening in the aerospace sector and how this is impacting metrology and quality assurance. We're going to discuss industry initiatives, standards, and ways that people can realize the benefits of Industry 4.0 in their everyday work. We're going to talk about things like tools and equipment, calibration, remote accreditation, and the skills and knowledge that you might require in the future. So joining us today to discuss these topics and answer your questions is Franz Helmli, R&D Director from Bruker Alicona. Hello, Franz. And Benedikt Krist, Product Sales Manager of X-Ray from Zeiss. Hello. So I'll just do some short introductions now, and then we're going to have a presentation from each panel member. We'll then go on to our roundtable, and after the roundtable, in the second half of the session, we'll have a Q&A session when the questions that you submit will be asked to the panel members. So Franz first. Franz has been a member of Bruker Alicona since the company's foundation in 2001. And he's played a role in the development of all of the company's 3D optical form and roughness measurement systems. The latest innovations of which include the optical coordinate measuring machine and optical lateral probing of components. Franz is also a standardization expert and active in international standardization. So Franz is going to give us a short presentation now, just about his area of expertise and Bruker Alicona. So over to you, Franz.
Thank you very much. I'm opening the presentation. Okay, here is, can you see my presentation?
Yes, Franz, we can see it. Yeah.
Perfect. Thank you very much. So I want to give a quick overview about Bruker Alicona. I'm from Bruker Alicona. So Bruker Alicona makes optical measurement equipment, and all of them are based on focus variation. We were founded in 2001, so we are now 20 years old, and we are specialized on optical coordinate metrology. The technology focus variation is established but not used by many companies. And here's a quick overview how it works. When you have an optics with limited depth of field, you can use this effect to measure 3D. So for example, when you have a camera and when you look at the scene, only some parts are in focus. In this case, the tree, but not the car. But when you then move in relation to the scene, other parts get in focus. And by combining the images that you acquire, you can calculate 3D data, you can calculate a sharp image. And this is how we do, how we calculate, how we measure in 3D. There are some limitations on focus variation. There are some limitations in general for optical metrology, and typically you measure from one direction and sidewalls cannot be measured. We have now an extension to focus variation, which is vertical focus probing, where we can measure also sidewalls. So when you think of a tactile instrument, you probe with a sphere from tactile. We can also do this with an optical sensor, with our optical sensor, and therefore we can measure holes. Our product portfolio is not only one product, there are several products. Starting on the right is an optical coordinate metrology instrument, very high accurate, very high resolution, top notch. And then we have our Swiss Army knife, the infinite focus. And you can also see many other small instruments for use in the field, use on a cobot, use for cutting tools, and so on and so on. So we have a whole product portfolio, but all of them are based on focus variation. We are talking here about aerospace, and I want to quickly hop over application in aerospace. So when you have an airplane, you have a turbine that drives the airplane, and this turbine consists of small parts inside the turbine, the turbine blades, the turbine blades, and these turbine blades get really hot on the hot part of the turbine, and so that normally the hot air is has a temperature that is above the melting point, and therefore the turbine blades have cooling holes, and cold air comes out of the turbine blades and cool the turbine blades. And these cooling holes are very important. And that's what we do. We are measuring the cooling holes. And with our technology focus variation, vertical focus probing, we can measure the top part of these holes and also the conical part and the holes of the turbine blades to ensure that the turbine blade will work. And so this is one application that we can solve. And also where our product is integrated in a production line, where it's interfaced with the production machine, where it's interfaced with the QS system. So something like Industry 4.0 that we also will discuss today. So that's my presentation for the introduction. So thank you.
Thanks, Franz. That's great. So I'll just introduce Benedikt now, who also has a presentation. So Benedikt joined the CT department within Zeiss in 2016 and has since become somewhat of a technology evangelist for X-ray CT, helping people to apply the technology in their R&D and also their quality assurance processes. Benedikt has a master's in mechanical engineering and a special focus on aerospace projects. Benedikt, over to you. I'm looking forward to hearing about this.
Yeah, thanks, Ben. Thanks for the introduction, and hi to the audience out there. Thanks for tuning in today. So my name is Benedikt. I'm actually a product sales manager for X-rays within Zeiss. I want to give you, first of all, a brief overview over Zeiss in general, what Zeiss does, and then about what solutions we offer within X-rays and what they could possibly do within the aero industry. So Zeiss in general consists of four main pillars. One is the semiconductor manufacturing, where most of the chips or where we supply the chip manufacturers with technology in order to manufacture chips. So you can imagine right now with the short supply in chip manufacturing, this business is growing quite well. It's quite likely that the smartphone you're using will have a chip which is actually manufactured with Zeiss technology. Then within the industrial quality and research pillar, where I'm and where the whole X-ray department is located at, and we have different solutions like CMM, X-rays, and so on. Additionally, we do also offer our optics knowledge within the medical sector, which means like we have robots for helping surgeons doing visual correction, like laser correction of the eye. And as well, we have our consumer markets where we supply the market with the end consumer, basically with the glasses to enhance their vision as well. Okay, I want to focus now on the industrial quality and research. Within the industrial quality and research, as I said, we have different types of systems: contact systems, optical systems, CT systems like X-ray systems, 2D X-ray systems, and as well all different sorts and types of microscopes, which Zeiss is well known for. But my specialization is within X-ray, and especially also X-ray CT. And with X-ray CT, you can make actually the invisible visible. So you will penetrate your parts completely and therefore have as well the external geometries as well as the internal geometries. You can evaluate on them, like looking for defects, as well doing metrology on internal structures, which you couldn't do with any other optical or touch probe system, for example. So what is our aim? Our aim is usually we look at the application our customer has, and therefore we supply the application or solve the application with different building blocks. Therefore, we have special systems in place. We have the required software for evaluating the results coming out of the systems, and as well accessories and services which are needed, for example, for doing service metrology, servicing the machines as well, and all sorts of accessories you could imagine, and what a real metrologist could need. So I already told you about X-rays in general. I was speaking shortly about 2D X-ray radioscopy. So basically 2D radioscopy is I would say the X-ray standard right now within the aero industry, well known, well distributed, where you only do a 2D X-ray image of your part, often used also for checking turbine blades, as Franz did already show them. They're not only to check the holes, but also to check inside if there are any residuals inside which would block such cooling holes, which would block the air flowing through the turbine blade, which would later on lead in heating up the turbine blade and also destroying the turbine blade. As well, also, yeah, and as Franz just showed via his hand, maybe also crashing an airplane, which we really want to avoid, actually. So as well, you can use CT tomography. Actually, from my perspective, the aero industry is working strongly to develop further in making use of computed tomography, as this gives us additional three-dimensional information. So with 2D radioscopy, you basically get a 2D X-ray image of your part, but with 3D computed tomography, you get the full 3D data, basically a digital twin of your part. And therefore, you can evaluate not only for defects, you can with CT tomography, you can now exactly localize the defect within the 3D volume. You can measure on your parts for certain geometries like wall thicknesses as well, also important for turbine blades. As well, you can do assembly checks when, for example, you have an fan blade with an MLE where MLE is glued to a composite material. There you want to check if there are any flaws within the glue. So if there are any bubbles inside, which might affect the working of the glue, basically. Then the third principle is the X-ray microscopy, which we also use. This one allows you to get an even higher resolution. So as you can see, compared to the computed tomography, it's basically also a CT, but computed tomography, there you have the X-ray source and a conical beam towards the detector. Because of the conical beam, it depends on where you put your part, depending on the location of the part between those two components, you will get different resolutions. On the X-ray microscopy, there we can also scan bigger parts, but scan small volumes of that bigger part and get a very high resolution, less than 1 micrometer, for example, in a few hundred nanometer scale, of a very small volume. Therefore, we use also optics, which would allow you to magnify this optically, and Zeiss as an optics specialist can really make use of the knowledge there. Both of them actually give you 3D data, one like more in a macro structure and the other one in the microstructure. With these three principles, we basically have the broadest X-ray portfolio, the broadest X-ray portfolio on the market right now. We do have like the X-ray microscopy, which you see here on the top right, for as lab devices, mainly for R&D purposes, where you could, for example, have a look at your coating thicknesses on turbine blades, as well as on compressor blades, and so on. You could also use the metrology product line, our Metrotom systems here on the top left, also lab devices. These two do allow you also to do metrology as well as inspection on in the same run. Basically, you do one scan and can do all at once. And then we have for inline inspection, we have especially our Volumex systems on the bottom left, which allow you to do very fast 100% inspection of your parts with a full CT scan, so giving you three-dimensional data. Or you could do just like, which is well known in the aero industry, do 2D X-ray imaging with our Bucello product line on the bottom right. So as you see, we have the full width of the portfolio, possibly really covering the entire industrial process from the R&D with the very high resolution up to the very fast image acquisition and evaluation with our Volumex and Bucello systems. So much from my side for the introduction. I give back now to Ben. Thanks.
Hi, thanks for that, Benedikt. Great, interesting to hear that introduction. So just briefly, I would like to encourage the audience to ask questions via the box on the right-hand side while we're talking now about metrology, and I ask the questions and we discuss during the roundtable. The questions that you submit won't be published instantly. I will publish them as I ask them in the second half of the session. But please don't let that stop you. Please keep asking questions. And the earlier we get them, you ask them, the more likely we are to have the time. We often run out of time. So I just wanted to encourage you to do that. So thank you both. Franz, I wanted to start with you. In fact, I'll ask this question to both of you in turn. But we seem to be talking quite a lot about using these machines in production environments, in manufacturing environments, production environments. Could you just tell me briefly first, Franz, I mean, what makes the CMM machine suitable for use in production environments? What are the kind of things that you're looking at when you're doing that?
So production environments typically are different to the laboratory environments in relation to temperature stability and vibrations. Our micro-CMM instrument is built of heavy granite, so it's less sensitive to vibrations. And also we use linear scales made of Ceradur that have no thermal expansion and inverse steel. So we put in a lot of technical stuff so that that the temperature doesn't influence a lot. And we also have put temperature sensors on critical points so that the operator gets the information, oh, the temperature is okay or is not okay. And also in relation to software, the operator or an administrator needs to teach in parts, and then the worker just put in a part, press a button, and then the machine is measuring. So the machine must be able to automate predefined sequences. And I think these are the basic things that you have to do to bring a metrology device into a production environment. And then there are other small pieces, but basically that's it.
Okay, thanks. Benedikt, you showed us several X-ray machines there. I'd like to ask, what are you, in aerospace, what are you most often supplying, and what are the kind of issues around it? What do you have to be careful of when you're using it? Is it
So the most supplied systems right now still are 2D X-ray systems, as this is kind of the standard within the aero industry. But of course, the challenge is like getting three-dimensional data, doing metrology and inspection all at once. So maybe also getting, sorry to have to say that this, getting rid of CMMs also within production sometimes. That's the aim actually of the aero industry, doing all at once. And the challenge there, of course, is still getting faster within the production. SCT, there, especially in the lab environment, usually you have plenty of time doing an X-ray scan, getting good data quality out of it. Within the production line, this available time really shrinks down. Like you want to get almost 100% inspection. In the aero industry, usually it's a 100% inspection. Therefore, you have to shrink down the time per scan. And in addition to that, what we see is the aero industry wants to scan larger and larger parts. So not only limited to the small blades, but also larger. larger parts, and this is of course still a challenge. As you might imagine, the X-rays are harmful to the human body. Therefore, this has to be enclosed, and you can't really get bigger and bigger with the machine size as far as you want. And also with the size of the component, there comes physical effects which might also limit the use of X-ray devices. So therefore, still there will be a good use for CMMs.
Okay, so there were two main parameters there. You talked about the size, but also you talked about the speed of the measurement operation, which leads me to my next question, really, about automation. I'll ask you both again, Franz. I mean, how much automation are you able to introduce into your measurement operations with CMMs and other machines? Is that something that you guys are working on?
So since the beginning of Alicona, automation was always very important. And now 2021, I think all of our steps in the measurement sequence can be automized. So maybe we show the video later that I've prepared, but loading of parts, selecting of programs, measuring the part, generating report, the whole procedure can be automized. So loading with robots is standard for us. What needs, where we're still working on, is the definition step. So to automate something, an expert needs to define the steps. For example, when you have a task to measure the hole, to measure dimension, an operator has to define where to measure, what to measure. And this is, I think, the final steps that where we are working at the moment to make this easier. But the rest is automized. It depends only on the budget of the customer, how much automation we provide.
Okay. Benedikt, what kind of automation are you able to put into your machines now?
Yeah, typically we would differentiate between the hardware automation, meaning like you have a robot loading the system. This is well known, I think so, also widespread through the industry. And on the other hand side, we do also work on the automizing the software evaluation, basically getting data out of the system and automatically evaluating the results which are coming out, the data results, the three-dimensional geometries, evaluating this automatically. Therefore, we're working on and further developing our already existing software portfolio with GOM Volume Inspect, which allows you to evaluate on the three-dimensional data, as well as also with dedicated solution for inline inspection, like our Zeiss developed automated defect detection software called ZADD. This really allows you to get like very, as you might you have to imagine, like you're scanning a full part, you have thousands and thousands of single points basically, and that's a really big amount of data, and you have to process all of this data. Finding the tiny defect within that big volume is really a challenge, and therefore you have to speed up that, and automizing this and speeding up that calculation is really a big task, which we have already solved quite good, I'd say. Mm-hmm. Yeah.
Is that the same with Bruker Alicona machines, Franz? Is there a lot of automation on the software side now as well?
Yes. So what I understood from Zeiss is that the analysis is automized. Yes, that's also what I said before. Depending on how you do that, an administrator specifies what he wants, defects or geometry. But then when it's defined, it's all full automatic. You get the same from us, because the Benedikt also mentioned GOM. For a specific task, we also use GOM. So this is something like an industry standard that we also use for some applications.
Okay, so the title of the webinar is Challenges and Benefits of Industry 4.0. Industry 4.0 means different things to different people, but I think we can agree it means to most people digitalization and data and machines talking to each other. And I mean, if you have another definition, now is the time to mention it maybe. I would just like to ask you, what do you see as the real benefits now to an engineer with utilizing those kind of digital tools, or the communication options that are open to them? What can they do now that they couldn't do maybe 10 years ago or 20 years ago? Franz, does that question make sense to you?
So the question is, what are the benefits for an engineer or a customer of our products or products to Industry 4.0? I think with Industry 4.0, solutions are now possible that were not possible 20 years ago when, for example, a robot grabs a part from the manufacturing machine, brings it to the measuring machine, and then the measuring machine knows, okay, it's that part, this has to be measured, and this is the specification, it measures it, then you get the information, it's okay or not, and then the result is stored into a QS system. And I think the last, let's say, 10 years, many companies are working on these solutions, and now we call it Industry 4.0. But this is the benefit, that this connection between the machines is now possible and works now more or less seamless, depending on the pre-existing technology at the industry.
Okay, sure. Benedikt, do you want to talk to that? I mean, what are the benefits in your eyes of it?
Yeah, actually, I would like to add a little bit to that. Of course, what we do is we inspect a certain part and we store the part related to like that part number, let's say. So we know exactly, especially in the aero industry, when we pull that part from our running engine, basically, what part is this? Where was it measured, and so on. We want to make sure we know this. In order to later on also evaluate, has this been inspected correctly, and so on. Was it produced correctly? That's the one hand side. On the other hand side, you still want to use the data you get out of your systems to improve your whole process. This means like you will have to collect all the data coming from different systems, collected all into one database basically, and making sense out of that. And for that, also Zeiss has developed a software tool, which is called PyWeb, which would allow you to collect the data from different machines, metrology devices, different sites as well, and make sense out of that data, making statistics out of it, making protocols out of it, which then allow you to derive measures to improve your process as well.
Okay, sure. Now, is there the requirements on metrology have changed, and are always changing, evolving over the years, maybe, what are kind of common challenges or problems that your clients, your customers will come to you with that need solving? Is that what's, I don't want to say the most common, but is there a theme among them? I mean, we've talked about data quite a lot. Is it around handling data, or is there any new requirements that people have?
So for us at Alicona, the most of the time when it's a hard task, it's not interfacing. So Industry 4.0 is 4.0 is very much about interfacing. The hard part is about what we get from customer is measuring such small tolerances, measuring such small geometries. Normally, when there is a measurement task, even if it's integrated, they don't come to Alicona. They come to Alicona when it's really hard, when it's really tricky. And then we have to measure small contours with very small tolerances in a very short time in an environment that is horrible. So this is normally, this is the hard part for us.
Yeah.
Okay.
That's basically also the challenges we see right now, seeing more details in less time, basically. That's, of course, with X-ray, especially with CT, that's kind of an issue. You have to speed up things. You have to have certain algorithms to speed things up, have to have the right machines to do this job as well. for seeing also the tiny details. That's a challenge, and as well, the challenge is still to combine the accuracy of a CMM with the full 3D data, basically. Yeah.
Actually, I'm also part of VDI in Germany, and there is a publication from VDI about Industry 4.0 and the challenges about it. And I've here the screenshot on my other screen. I also can share it if you like. What is the outcome? It's one slide of this. What does Industry 4.0 mean, or what are the challenges of Industry 4.0? Is it okay to share with you?
Sure.
So give me a second, please.
I do have some questions in. They're coming in via the private chat. You should be able to do it via the box on the right, via the Q&A tab. So I'd encourage people to do that. Anyway, please continue, Franz.
Okay, so this is the result of a big survey in Germany of members of VDI, what Industry 4.0 means. And actually, the writer of this publication, they're all from the VDI, and there is also Mr. Berthold, and also a guy from Zeiss, and which is Mr. Imkamp. I know him very well. Yeah. And the conclusion is, Industry 4.0, the challenges in this is faster measurements that are more accurate, that are more reliable, from instruments that are more flexible, and what you have mentioned, Benedikt, is the holistic view over it. So this is what the industry searches for. Faster, more accurate is very important. Reliable is the production environment, and flexible is to react on changes and to react on different parts with different specifications, smaller batch sizes, and so on. So this is the direction it goes, and these are also the challenges. But I think, as Benedikt also said, faster and more accurate, I think, is the biggest challenges for us.
Yeah.
Thank you very much.
Okay, thank you, Franz. Benedikt, do you have anything to add to that, or?
No, I think like we've captured the image Franz has shown already in part, and now we've got the overall overview. What also the industry says and concludes what Industry 4.0 means in total.
Yeah. Excellent. Well, we've got some questions in already. So we've been at roughly over 30 minutes talking amongst ourselves. So let's hear from the audience. So I have a question here from Stephen Johns. Stephen asks, what would be an estimated cycle time for 100% inspection of a turbine blade with cooling holes approximately 4 inches in size? What is the demonstrated inspection accuracy of the systems, i.e. blade fir tree inspection with tolerances of plus or minus 0.001 of an inch? So that's quite a long question. So we'll start with the top. What would be an estimated cycle time to inspect a turbine blade with cooling holes 4 inches in size? Anybody want to take a stab at that?
So it kind of, if I might start.
Yeah, sure. Is it too general, or?
It kind of depends what you understand under inspection. I mean, inspection could be like only looking for defects, only looking for residuals. This could be done quite fast, in a matter of a few minutes, basically, per blade. Let's say roughly 2 to 3 minutes, maybe. If you really also want to look for doing, at least at some part, also metrology, like wall thicknesses and so on. For this case, you will certainly need a little bit more of time, like maybe 30 minutes or even more. Depends on also the material of the part, especially for X-rays. The type of material is quite important. The denser the material, the more challenging. And of course, turbine blades usually are made of Inconel or also of titanium or so. These are quite challenging materials for X-ray. Therefore, it always kind of depends a little bit on the real blade we're looking at. Yeah.
Okay. So, please, Franz.
The question was about the 4-inch blades. What we do on 4-inch blades, typically 1-inch to 4-inch blades, is measuring of these cooling holes, and therefore the amount of cooling holes in such blades is between 50 and 200. And we do this in 15 minutes to 1 hour to measure the cooling holes. We have other machines to measure defects on the surface, and this is in a range of 15 to 30 minutes for such blades.
Okay, this second half of the question, what is the demonstrated accuracy of the system? Does anybody want to answer that, Franz?
If the question is the overall geometry, we typically, this is an easy task that is solved already. We don't have customers to measure the overall geometry because it's easy. And I think he says a thousandth of an inch, which is 25 microns. And this can be done, for example, with a gum machine. And I think such machines can do the job. When we measure the cooling holes or some defects in cooling holes, our accuracy is much less. Then we have errors in the range of 1 to 2 micron.
Okay, thank you very much. I have a question here. I'm not too sure who it's from because it's come through on the private chat, but it's from, I'm going to call him Anonymous. He wants to know about gear cutting, measuring when processing gear wheels. With a hone or grinding wheel, can anyone talk around that? I mean, is that a particularly challenging application, gear cutting or measuring gears after they've been produced? Is that an application that's come across anyone?
So, Benedikt, you first, or should I start?
I'll let you start. Go ahead. Thank you.
The gears is a whole different world. And there are so much different things that needs to be measured on gears. One is the flank geometry, for example. Specifically, we have the option, a software module built in to measure the geometry of flanks on gears and evaluate all of the flanks on the gears. We call it the all-tooth method. To measure it, but the question is, what is the size of the gears? If the gears are small, then we are the experts. So when it's tricky, and if the gears are larger, then I think there are many machines that can do it. Yeah, there are many out there, and maybe Alicona is then not the right. But if the gears are small, in the range of 10 millimeters, 20 millimeters, or sub-millimeter, then we are the expert. And dual tooth geometry, flank geometry, I think is the task that everyone wants, and we also can do. Yeah.
So typically, when you're talking about gears, I think the one who raised this question was thinking about steel gears or at least dense metal gears, and therefore, usually, as Franz already said, you want to measure outer geometries, which you can do really well, highly accurate with a CMM or maybe also with an optical system. X-rays wouldn't really be the right system to do this job. In that case, as usually X-rays are used to evaluate materials or internal structures. Of course, you can do also the external structures, but then you oftentimes go for a CMM, especially when you have like dense and very challenging materials, at least for X-ray, like steel.
Yeah, that's. I wanted to ask a question about that, Benedikt. Actually, I mean, are there any? I mean, what advantages does X-ray metrology offer when you're talking about different materials? I mean, materials is such an important area in aerospace. You know, we're always innovating in that area. I mean, you talked about challenging materials there. I mean, is that an important area for you, looking at the capabilities of X-rays?
Yeah, of course. Like especially in the when you're looking at our microscopy CT systems, there you can do like look at the tiniest of details on your materials. Like for example, especially when you have additive materials, looking at the powder size, grain geometry, and so on. This, for example, as well, when you have also molded parts or composite material parts, you could inspect the fiber orientation, delamination between several slices, and so on. These are things you could do really well with an X-ray, especially CT system. Yeah.
Yeah. Okay. Whereas a Bruker system, CMM, it's really at the other end of the scale. Am I right in thinking that, Franz? You're talking more. I mean, what are there any limitations there, or it's not? Not really.
Yes, less. So the material, so we can measure from glass, silicium, steel, plastics, but we are measuring optically. So there are some optical effects when the material is translucent, when it gets hard. But this doesn't happen very often, because in industry you have metal parts, and focus variation, our instruments are built for metal parts. So normally the material is not an issue.
Mm-hmm. Okay. So I have another question here from the audience, again from Stephen Johns. He wants to talk about automated inspection, automation. Is there a requirement for cleanliness when you're talking about these machines and automation? And are there automated filtering options, he asked? I'm not really sure about the context of that, but it's a good question about cleanliness.
So for us, when we measure microgeometries with optics, so we have to look at the geometry, we have to see them, and when there is so much dust on it that we can't see the microgeometries, then it gets hard. So normally, when it's critical, parts are cleaned with compressed air, brushed air, and then the biggest parts are gone away. And but they are always for small tolerances and small features, there are always parts on the surface that shouldn't be there. So we have to deal with them. And for example, when you measure geometries, what you do is you measure the part, you get 3D data, you get millions of 3D points. And out of the millions of 3D points, you then generate a digital twin. For example, you fit in a cylinder, you fit in a sphere, you fit in a form element. And this fitting procedure needs to look at the points and look how does this geometry element fit in. And there are different procedures available. There are standardized procedures available, and normally they are crap. And there are procedures available that are used in real world and that are more, let's say, reliable in relation to defects. So they look on the surface, they identify that there is a defect, there is a dust particle, and don't use these 3D points and only use the rest that are that belong to the structure, that belong to the form, and that then get a repeatable result, and then will give a procedure that is, let's say, capable.
Yeah. So I think that there are maybe two more sides about the cleanliness of the environment, or technical cleanliness within the production process. One would be, for example, is the system suitable for that environment? Meaning, like, are the axes well equipped for being in a rough environment and so on? Or is the whole system stable under these thermal conditions and so on? This is the one hand side. Of course, there are special systems with special housing and so on for being run in such a rough environment. On the other hand side, when talking about technical about cleanliness, you could also think about, like, finding that dust within your part, or finding that residual within your blade. This could be something that could be actually done with an X-ray CT. So you can also solve or maybe find this issue with such a system. And making sure, like, you don't have these particles within, like, for example, in the battery industry, that's a really tough job, or a real challenge to find particles which don't belong inside of a battery, for example, which might result in short circuits and so on. Therefore, there you want to find such particles which don't belong there. Also within the turbine blades, which are oftentimes casted, and you want to make sure that there aren't any ceramic residuals inside anymore. This could also be kind of technical cleanliness. Yeah.
Okay. I'd just like to ask, are there any particular case studies, any problems that you solve for clients that you'd like to highlight, that you're particularly proud of, that you're proud of your company having solved for a client? Any real tough problems? Franz, you look like you might have one or two stories.
I have a video. I've prepared a video, and I think maybe this now fits good. So
Okay.
can I show it?
Sure. If you can work the buttons. There we go.
So I play now a video of an application. So I mute the down, and what you see here is a production environment and a robot, and you also see our system. So the robot now moves in this production environment and moves now to our microscope. And what he does now is he grabs a specific sample holder and brings it to our instrument. And this specific sample holder is a fourth and the fifth axis. So our instrument has got 3 axes, and for a specific application, they load a fourth and the fifth axis. So this is now loaded from the robot, and this is loaded with really high accuracy with a 0-point clamping system. And then the robot grabs a part from the machine. I think it's a grinding machine in this case, I'm not sure. And he grabs the part from the grinding machine, and the robot now moves on the other end and puts the part into the 0-point clamping system of the fourth and the fifth axis. In this case, you see an EDM electrode. And now the measuring happens. So, and also the robot can load a different sample holder. In this case, a big blade where you can mount other parts. And this is, I think, a good example about Industry 4.0, where we have a production environment, an unmanned production environment, where there is a process that specifies what is produced when, and then the measurement machine is fully integrated, and also sample holders are automatically loaded with a very high precision. And I think this is a nice solution.
To integrate that into a production line like that, Franz, I mean, how long a project did that take? Was it was it months? Was it a longer time? It looks hard and expensive.
Normally, yeah, more. I think you get in first contact with a customer, then there are first discussions. So till the order, in this case, normally you have 6 months to a year. When it's ordered, till you ship the solution, it's also for something like this, 6 months to 9 months. And then you have the procedure that you work on the customer side that everything works, and this can be some weeks, and in the worst case, maybe also 2 months till everything works. So from first contact to the final solution, you worst 1.5 years, 2 years.
Okay. So what kind of benefits did the customer receive from using that system?
One benefit is that he can change what he's produced, including quality control from remote. So he doesn't have to go there. Also, the calibration is integrated. So the robot can load also the calibration tool. And so also, whenever the measurement machine is standing still, it can do a calibration and checking itself.
Okay.
And also that the operator maybe makes no error, because there is no operator when he brings the part from one machine to the next machine and is starting the wrong program to measuring this part. So there's less operator influence, less error on that. And also in such an environment, you can have let's say an overview, a management board where every data is aggregated and shown on one screen. This I think benefits for the industry, for the customer.
Yeah, very, very useful. Thank you. Benedikt, I pass this to you. Do you have a story, a particular story? Maybe, I'm not sure if you had a video, so maybe describe with words.
No, actually, I haven't. I don't have a video prepared. Of course, those videos showing like full automation are always nice to see, and these are really like the big projects. But to maybe give you also another insight, what we as Zeiss, I think, can be really proud of, especially when we're talking about Industry 4.0. It's oftentimes also about additive manufacturing. Also in the aero industry, in the medical industry, and so on. Everyone's working on additive manufacturing. And we as Zeiss, we really created a complete blue line of products, which we call them, which allow you to monitor your printing process basically from the powder until the end, the final end of your product. And also as well allowing you to have, like, when you, for example, have a blade printed, let's say a compressor blade, inspecting with an X-ray CT, inspecting the blade for any defects, for any pores inside, and before the machining process, the post-processing basically, you can do that already to find out if it will be a scrap part or not. And in case if there is a defect, having a look at the defect with another system, basically this could be like electron beam microscope, or this could also be an X-ray microscope, having a higher resolution in that specific area and then correlating the data, having a look at the tiniest detail of this defect, and then also maybe getting back on how to improve the process again, how to get rid of such a defect, and also maybe finding out how this defect could even occur. Yeah.
Okay, right, great. Thank you. Interesting points there. Thank you. So I'd just like to give a last call for any questions. This is the last 5 minutes. So if anybody has any, now is the time. But I mean, just to sum up, it's been great to hear about these solutions and how the new types of technology that you have at your disposal really enables some of the things that engineers are able to do and making things more efficient and improving. We perhaps take this last one from Stephen Johns again. He's just asking about CT evaluation of coating thickness or surface cracks. Is CT evaluation of coating thickness or surface cracks accepted by the aerospace industry as a replacement for cut-up inspection? I mean, has it done? Is that more of a standards and certification question, really?
Sorry, I didn't get the second part of the question. Sorry.
Is it can we accept CT X-ray evaluation of coating thickness or surface cracks as a replacement for cut-up inspection, as a replacement for destructive testing?
Usually not. The parts which are coated usually. What you do right now, like you cut them, put them in epoxy, grind them, and have a look at them under oftentimes a light microscope to measure the coating thickness. Then you get only the coating thickness in only that specific slice. What you can do with an X-ray CT, still you have to cut it, as oftentimes the parts are quite dense and quite big, and you want to really see a high resolution. Therefore, you only want to have a smaller piece of it in order to get that high resolution. But the benefit what you will get from an X-ray CT is like compared to when you will have to put the complete part, the cut part into epoxy. This will take like 24 hours to harden and so on. You will get your results at earliest the next day, I'd say. With an X-ray CT, you can cut it, put it in the CT system, do a high resolution CT scan of maybe also a few hours, but still you will get the results at the very exact same day. So really, this gives you an improvement in time, getting to know your process better earlier, and therefore also allowing you to readjust earlier.
Okay, thank you very much, Benedikt. Franz, I mean, have you got anything to add to that, or probably not? No. Would you like to? Have you got anything you'd like to conclude in? Any concluding remarks, guys? Franz, have you got anything you'd like to sum up? A summary?
Any message?
So I think I can say something to Industry 4.0. Industry 4.0 is connecting machines together, and everyone talks about it. And in my experience, there is no established standard for connecting machines together. So one says this, one says this, one says VDI GDX, one says OPC UA, one says DIMS, whatever. There is no standard, no implemented standard that is really used in industry to connect machines together. So what I want to say is, I'm also working in the standardization committees. I know that it takes a long time. So I think everyone that can influence this should do it, because it will have much more importance in the next 5 to 10 years, I have to think. And we can all benefit from it if there are standards that are implemented to bring the time from first contact to deliver a solution down, because this is a lot of work, communication, implementation, and this can bring costs and time downwards. So everyone that can influence this, please do it. Thank you.
Good point, Franz. Nice place to finish. Benedikt, do you have any concluding remarks you'd like to make?
Yeah, I think in general, metrology is often underestimated in what it can bring to the table in general as a add of value. Oftentimes it's only seen as an expense, but actually I think metrology is actually an add of value, as you can later on improve your process, improve your quality, and down the road it always pays off. So therefore, I think to all the metrologists out there, keep on working, keep on improving your processes. And in any case you might see challenges, please reach out to me. I'm happy to help wherever I can. Yeah.
Okay, thank you. That's great. It's another good message to finish on. Oftentimes I hear from different, not just metrology, but different aspects of aerospace testing, the sort of cause that the testing shouldn't be seen just as a cost center, but also as value, that there's value in the data that people that people produce, that engineers produce, and it's realizing that value and extracting that, which is so important these days. Great. So this session, this webinar will be available on demand afterwards. Everybody that registered or watched will receive a link, an email link to the Big Marker platform where they can watch it again. It'll also be published on the Aerospace Testing International website for people to access afterwards. So please do check it out if you want to again. Okay, great. Well, thank you, Franz, for your time, and thank you, Benedikt, as well for your time. It's been a very interesting chat, and thank you, the audience, if you've watched this far. That's fantastic. Yeah, have a great day. Cheers.
Thanks, Ben.
Thank you. Bye-bye.
See you. Bye.